work and I need to do the new one. So it was some unexpected. Okay, I again need to switch on. No. Okay. So it looks that I put everything that everybody can come in without any permission. I hope it will work. So if somebody will have a problem, please write in Telegram. Okay. Thank you very much that you allowed to me to pass this lecture for today, because I really was in travel and couldn't give a lecture on Monday. Now I will share my screen. We can continue. And please remind me to make a screenshot with all students who are present on the lecture. And I could see today I received finally the list of the students, and it's a lot of students, like 50, but I can see that only now how much? 13 now present. Okay, so again, I would like to tell that I take into account the presence on the lectures. It's working. Okay. Okay, this one. So so I will remind. So can you see my my screen?
Yes.
Yes.
Fine. Okay. So I will remind that we are now working with a principle with cosmology, and so we discuss the observational properties of the universe, and what we did. So we discussed cosmological redshift. So we discussed that all galaxy has a redshift in the spectrum, which tells that they go out from us, from observer. Also, we formulated Hubble law, and we proved that Hubble law, so the linear dependence between velocity and distance to the galaxy, is a result of the homogeneous and isotropical expansion of the universe, expansion and go away of the galaxy from us. Also, okay, let's continue. And we finished on the point to prove that really the universe is a dark, not only from the point of dark energy and dark matter, but also if we will consider the distribution of stars. And let's consider how prominent or which is power of energy we will have in the, for example, if we will choose some cube with, so we have a universe, we can choose some volume with a mean distribution of matter inside. As a matter, we will consider the stars, and let's estimate which density of luminosity we will have in this volume, to understand how bright is the universe if we will consider it as an average distribution of the stars. So we already discussed that distribution of matter such a way that we have a structure like a spider net, okay, like this. So I showed you some simulations. This is like Again, here we have some, it's of course schematically, but so like this, okay. And this is, we believe that this is cluster of galaxy clusters. This is filaments. In cluster of galaxies, we have some also active galaxies. So if we speak about active galaxies, galaxies which have a huge supermassive black holes in the center with high production of energy due to accretion, like this. So they are located usually in these regions. We have a thin filaments here, for example. Here, these filaments also consist of stars and gas. Of course, the cluster of galaxy also consists of a lot of gas. But what is also important that we believe that there are such a kind of voids here. So this is voids. Where we don't have almost matter. So it's an empty space. And now we will look, we will estimate if we will suggest that all stars distributed homogeneously in the universe, or all stars from such a structure, we will distribute like a homogeneous distribution. Let's estimate which finally we will have the density of luminosity. Okay, for example, we know from observations that the density of luminosity is approximately 10 eighth solar luminosity per megaparsec in cube. Okay, this is from observations. If we will remind that English. Just a second. Okay, if we will remind that 1 watt equal 10 in 7th erg per second. So the same expression, the same value. Okay, I will put here equal, here equal. Approximately. So we can estimate. So it will be 10 8. After this, also we will remind the luminosity of the sun. So I put here the index, and this index is the index which marks the sun, equal to 1033 erg per second. In principle, I can forget about 2, so it's not so important for now. I put approximate equality, and I can write 33. So maybe in this case, we can suggest that all stars has a luminosity which is equal luminosity of the sun. Of course, it's not right, because stars are different, they have a different luminosity, but to estimate it's for this point, it's enough. Megaparsec, so mega, this is 10.6, multiply 1 parsec equal again, approximately, it should be 3, but for us, it's not important. I can immediately write here because I don't want to spend time for this. Okay, 10, 5, astronomical unit. And in cube. Yes, for now not. I have my lectures. Yeah. Grazie. See you later. Okay. And what we have? We have 10, 8. And we exactly obtain 1033 divided on 1033. And this is erg second. Okay. So which is equal uh, 10 in the eighth, so it means that 10 watt per not right because erg per second, and divide. Let's write like this. Is follow for me, and if I made some, some mistake by chance, please tell me about this. Astronomical unit cube. So, and finally we have astronomical unit cube. Okay. So we can see that the universe really is not a bright place, because the average density is equivalent to the just one lamp which are using house. So you can see, we use a lamp 40 watt per 40 watts. So, and this is, you can see the very low energy power here. So you can remark in your conspect that really the universe is not a bright place due to the fact that we have these voids, these huge regions where we don't have enough matter. So the matter distribute, as I showed here. This is for curiosity, just to understand. Okay. If you don't have, yeah, well, I would like to say that it's a fortune that we are living in the bright place. We are living in the place where we have in vicinity the sun, and really, this case, the life can exist. Of course, if we could be here, so it's a cold and dark place. Okay, if you don't have equation about observational properties of the universe, we will start to work with the next point with Newtonian cosmology. Do you have some questions? Are you here?
Yes, we're here.
Okay. Okay. If you don't have equations, so let's continue. And we can so we can put a title of this lecture. Newtonian, I can call like this, cosmology. At one point, this is for curiosity, because in principle, we can formulate and we can obtain some result even using just classical mechanics. It's very useful because when we finally, we of course will work in the framework of general relativity, and we will obtain the solution of the Einstein equation for our universe and for cosmology. But it's also important to understand what we can see from classical mechanics. Why? Because in any case, and later we will again to come back to this question, when we obtain the solution in general relativity, of course, all time we need to compare it with the classical mechanics and to see which is the differences. This is important because we, in this case, we can be sure that what we did is right. Because in any case, for non-relativistic case, for post-Newton, it should be correspond to classical mechanics. How we will formulate our problem in framework of Newtonian cosmology, Newtonian mechanics. So let's consider some volume with a spherical shape. Okay, red. Not on one red. I want blue. I'll come back to blue. Spherical shape with a radius. Okay, r, which is in principle will be the function of t of the time. We can suggest that the mass which is inside of this volume m, and this is constant. So we will not consider that mass appeared due to such a fact. So we will consider the closed system. And the main question, so let's find the acceleration. You can write in your conspect. Let's find the acceleration of the particle which is located on the surface of this sphere. On the surface of the sphere. So we also will take into account that the evolution of this sphere of velocity has a linear dependence on the radius. So you will see now. In this case, on the particle will act the force from the point of the mass m. Very simple, we can write it. So this is dv by dt equal minus gm r squared. So it's a Newtonian law, okay? We also will use the fact that we have a homogeneous isotropical evolution. So in this case, as we already discovered, we have a Hubble law, and Hubble law tells us that where V, which equal dr by dt, equal h multiplied on r. So if we will put this one in this equation, we will have d by dt h r. So what we have, and we remember that h depend also on time. So we will have r h by dt plus h r by dt. So, and we have r dh by dt plus, and dr by dt, this is h on r. So we have h squared multiply on r. Okay, here we applied Hubble law. So if we will put this in the left part of this equation, we have that r dh by dt plus h square on r equal. And here, instead of m, for us, it's much more convenient to put expression through the density. So, okay, m equal 4 pi divided on 3 rho r cube. So, and I immediately will put it here. It will be minus 4 pi divided on 3 g rho and r. Or from this I can obtain the equation for how change the Hubble constant, which is Hubble parameter. Well, in this case, it's better to say Hubble parameter because as I will remind, so if h is a function, in general case, h is a function of time, and we call it Hubble parameter. Yes, and h0 equal h on the present moment, and this is Hubble constant. Okay, so we can write that dh by dt equal minus h square minus 4 pi divided on 3 g rho. So this is one of the equation which allow us to obtain the equation for for Hubble parameter. Of course, when we have some expansion and we understand that under influence of the gravitational forces, this sphere will evolve, this volume will evolve, and of course it will change of the density. So, and we need also to obtain the law how change density in such a case. So let's find the equation for density of the matter. In principle, what we can do it simple way. So we can write what is the density. This is m divide 4 pi 3 r cube. From this, we can, if we can find the derivation, the rho by dt, we have, okay, we have 3 divided 4 pi. M is a constant. We put just the m. And we need to find the derivation of 1 divided r cube. So it will be minus 3 r4 dr by dt. Okay, so we have finally, and I want to keep 4 pi divided on 3, so I will write like this, minus 3m divide on 4 pi on 3 r4 dr by dt. Okay, so again we will apply, and I would like to say cosmological principle, homogeneous and homogeneity and isotropy of the distribution, which again, and I will repeat all time, means that we have a Hubble law, and so this is it means that again we can dr by dt. I put it before, but I will repeat it. This is h multiplied on r. So, and if we will put it here, we will have d rho by dt equal And look, I can see here that I will come back. No, it's not a good like this. Okay, so I will write here minus 3 m divide 4 pi 3 r cube, which I can see that this is density, and I have 1r multiply HR, so I will have only H. Okay. So finally I have d rho by dt equal minus 3 rho multiply n h. So this is equation which determine how the dependence of density, if you will solve it, dependence density on the time. In principle, we can obtain such equation different way. So we can consider continuity equation. Okay. Continuity equation. So continuity equation, d rho by dt plus div rho multiply v. We need to put vector equals 0. You remember this equation, I hope. Okay, and when we say that we have a homogeneous distribution of the matter, it means that density doesn't depend on R. It depends only of time. In this case, we can consider, let's consider separately, divergence div rho multiply on v equal, so it's understandable that we in this case can take out density outside of the brackets. So, and we have rho multiply on div v, and again we will apply the Hubble law. And I would like to say that when we use the Hubble law, we can put it also in vectorial form, not only in scalar form. So in principle, in general case, we need to write v equal h multiply on r. Okay, maybe it's better here to write. So now I start to use 2r, which is not a good. Let's put here r big. Okay, so and in this case we will have rho minus plus rho h, and we need to write d by dx on x plus d by dy, and for z. Okay, so we will obtain exactly number 3. So we will have 3 rho h. And finally, we also come So, this is I can write direct derivation, so it's not important, but in case I can keep it here. So we have d rho by dt equal minus 3 rho multiplied. So we obtain the same equation, but a different way. And you can see, you can control what we used, which suggestion. So we put again the cosmological principle here. And cosmological principle together give us from one side the property of homogeneous to be universal, to distribute of matter by homogeneous case. And also it gives us the information about linear dependence between velocity and distance to the object. And as a result, we obtain such a kind of equation. Okay,
can I ask some questions just for clarification?
Of course.
So here we have this rho. It's density of matter in this sphere with radius r?
Yes.
Or,
Yeah, look, because we put here exactly, I will show here. So we, the determination of the mass, which we put here, this is a mass inside this volume. So the rho, this is the volume of this mass divided on scale in cube. If it will be a surface density, in this case, dimension of this surface density will be different. Yes, and there is we will speak about later a little bit about some curiosity and why, Newtonian we can't use Newtonian cosmology for the real cosmological models. It's can be considered only some as such approach only. It's the same as, for example, Doppler effect. Again, you need to remember that we can use the formula of the Doppler effect, but we need to remember that cosmological redshift, this is not related with Doppler effect, but we can, for example, use the same in this case. Okay, now I would like to investigate the evolution of the solid sphere. So it's better to say, in English, there are terms. In Russian, Ukrainian language, so we use a ball, which we would like to represent that this is some volume, three-dimensional volume, okay? And we tell sphere, which we would like to mention that this is two-dimensional, this is surface. In English, usually used the terms which is sphere, which means that this is two-dimensional surface, and solid sphere, it means like a ball. So it's a three-dimensional one. So I will use this, I can put it here. So here we consider solid sphere, okay? So in solid sphere, it means that this is filled with a matter. And this is three-dimensional body. Okay, so if we will put here particle, we put it inside, and this particle has three coordinates. If I say just a sphere, it means that this is two-dimensional body. So I say about surface. Okay, understandable. And the point has two coordinates. But later we will work with different dimensions, so on. Okay, now I want to investigate the evolution, this solid sphere. In principle, evolution solid sphere, but again, this is some such trick. So for us, it's also interesting much more when we say about such a kind of problem. I'm going to put it here. So, in principle, the evolution of the solid sphere tell us, of course, about evolution of the sphere. of the two-dimensional surface which bounded, which limited this volume. So in principle, what for us also interesting in this problem that from two body or two-dimensional space, that if we will have such a particles on the surface here in the center, we consider observer. Not obviously in the center, it can be also on the surface. So how how the galaxy also will which evolution of the galaxy will be if we will consider the surface, also the surface of this volume. Okay, let's write equation. I think from equation we also will understand better. So I want to write, to do this, I want to write the total energy of such a system. So this is simple kinetic energy, and I dr by dt square minus gm. Again, you understand that g, this is gravitational constant, of course. So, and I put potential energy, and this is constant, which is equal to total energy of the system. So in the first, I would like to find, to express the total energy. So the total energy in this, understandable, this is constant, and we can find the total energy due to some initial conditions. Initial condition or some properties of the system on such a time. So, for example, I can put the present time. For us, it's much more useful because what we observe, we all time would like to connect it with the present time. So, present time t0, and let's we know from observations why we would like to use the present time, the Hubble, and here I tell constant because I put 0 and rho 0. So in this case, the velocity of the object is h0 on r0. In this case, we can obtain the expression for energy, the value of energy. So this one divided by 2, kinetic energy, okay, so dr by dt square t equal to t0 minus gm divided by r0. So in this case, since we will use this one, below, I will have 1 divided by 2 h0 square r0 square minus gm divided on r0. So now I put it in these equations in energy conservation law. I will have 1 divided dr by dt. Now, for now, as you can see, everything is simple and nothing complicated. Later, it will be a little complicated, more complicated, but in any case, I hope it will be understandable. So, and right side, don't make a mistake. Okay. What I also want to do, I want to find, so my goal to find equation which allow me to obtain R as a function of t. So I want to understand, so this is R t, how this solid sphere evolve during the time, and which also tell me information how the surface of this solid sphere will evolve. So, and also, you know, about mass. Mass, it's not useful because usually when we make some observation, we say about density all time, so we can estimate the density. And again, instead of the mass, I want to put density, and I will put from on the left part dr by dt. Okay, square, I will keep square, not to use square root on the right side. So equal, and on the right side what I have, I think how it's better to organize it. And to attention, make an attention that here are 0, but this is here only R. So I want to put mass. It will be 8 pi divided on 3. G, because I will put M 4 pi divided on 3 R0, R0 cube. Okay, so and it will be G rho 0 R0 cube divided on R. So this is R, which is function of t. Minus, now I will put here this summand, so it will be also 8 pi and divide on 3 G, and here we will have R0 to rho 0, okay, and plus H0 L0 square. So now I will gather the sum and the terms which is which has a joint multiplier. So I put dr by dt square equal, and I can see that 4 pi divided on 3, and no, I will do different. I will now, you will see what I will do, because the first summand I will leave like this, like it is. So. Right on R, but the last two, since they don't have, I join them, since they don't have the dependence on R, I would like to join them. So I will write, it will be minus 4 pi divided on 3, 0. No. Square. Here I put rho 0 minus, and here I have 3h0 square 4 pi divided on g. Okay, we can put it in a frame, because this equation will tell us something, some story about evolution of the universe and about possible models in framework of the Newton and classical mechanics. So the first, what we can see that if we will go from formally, we will see that if R, so this is R, 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 this tend to 0, we immediately can see that dr by dt tends to infinity. So r tend to 0, it means that this solid sphere became smaller, smaller, and smaller. So we go to the past, and it means that the velocity of the object will increase if we will go in the past. This is the first. The second point, which we also can see, that here we also have here. This summon, the storm, has a dimension of density. So it's understandable because here on the left we have here rho 0 and it should be density. In principle, we can even check it so to be sure that everything is okay, but you can check it really. Most is 0. Should be 0 here. Okay. So let's call this this density, it's called like a critical density, C, okay, this index, so equals 3H0 divide 8PG. We understand that this is such a constant because H0, this is Hubble constant for present time, and approximately we understand that H from the observation we know that this is approximately. We will speak or maybe later, which is it can be 68 for now from different observation, but approximately 70 kilometer per second divided megaparsec. So we know this constant from observation. Also, we can know what is the value of gravitational constant, and we understand that this such a value of the density. And also we will use, by the way, we will use the relative density, which usually call omega in cosmology, and we'll put it omega 0. What is omega 0? This is rho 0 divided on rho critical value of density. So, and if we will include, if we will use this notation, we will rewrite it such a way that from this that dr by dt square equal, okay, this I need to rewrite, G rho r cube divide on r minus. So, and if I took out this, take out this outside, it will be h0 square r0 square. Okay. Omega 0 minus 1. So this is also famous equation which happened. So like this. Solution of this equation allow us to obtain, as I already said, the dependence R of the time, and also what we can see. So we, in principle, this is correspond to the this equation you can obtain from classical mechanics, this is famous two-body problem. And as you know, and exactly when we would like to understand, if you push some bullet, you would like to understand on which orbit this bullet or this test particle will move into body problem. And as we know from classical mechanics, there are two possibilities. When energy negative, it corresponds to elliptical orbit. If energy positive, it corresponds total energy positive, it corresponds hyperbolic orbit, hyperbolic motion. And if energy equals 0, this is parabolic motion. The same here. So if you will solve this equation relative to R, we will discover the following three cases. Let's consider it here. So there is three possibilities, and in Newtonian cosmology, it called three models of the universe. The first one, when this, for example, omega 0 more than unity. So, but you know, there is such a miracle here, because we just obtain some, I will put it even in red. We just obtained, we did everything right, and we just obtained some density, critical density, which depend only on the Hubble constant, and depending on the situation, the density of the universe, more the average density of the matter in the universe, more or less this critical value, the universe will evolve different way. And we will see now which way. So this is such a, you know, not cause miracle, so you controlled everything. What is also interesting that when we will work with relativistic theory, we again will obtain such a kind of relations. Of course, we will have also dark energy, lambda constant, but in principle, you will see that finally the expression is really not really similar. So let's consider the first case, omega 0 more than unity. So it means that the average density in the universe are for 0 more than critical. Okay. So in this case, what we can see that this the summand is positive and this is minus. This correspond. You can solve this equation here. So I will write schematically what we will have in this case. So in this case, if this is T, this is R. The solution of this equation, this is just a trigonometric function, sinus or cosine. So this is periodic function, and in principle you can see it quickly. So we will have such a kind of evolution. So I put here, I can write it out. We will obtain more detail in relativistic case. Here I don't do attention much more for the solution in classical mechanics, because in any case we will consider it much more detail in relativistic case. So, but in any case I would like to put proportional like a sinus. So just schematically to write that it's a sinus. Of course we need to put some dimensional things, so I will put it just like if this is T0, the present moment, so, and here future, and here past, like this. So what it means? It means, and this model called open universe. Oh, sorry, why open? Closed. Closed universe. So what it means? It means that in such a kind of, for this condition, if we, for example, has such a kind of evolution, the universe will start from some point, expand, but starting from some point which correspond to maximum, will start to collapse. So this is a solution why it's close to, which call it close to universe. So the second, and in classical mechanics, it's corresponds to the case an energy less than 0. So energy has a total energy has a negative value. So it means, I will put here by yellow in the first formula, that potential energy more than the kinetic energy. So if you push the bullet and there's some gravitational field, it will come back. So this is the idea. And this corresponds to body problem. This corresponds to elliptical motion. Okay. So okay. So the second solution, the second model, this is when omega 0 equal unity. In this case, exactly we have a situation when rho 0 equal critical. And so we have by the way, I would like to in advance to tell that in a relativistic case, this case corresponds to the universe with the maybe it's better not to say about it early because I need to take to say what is key later. So and in this case we have a we call it flat universe. So in this case we will have the beginning and expanding of the universe with the time. So this is flat universe. In classical two-body problem, it corresponds to the case when energy equals 0, so potential energy equals kinetic energy, and this corresponds to parabolic motion. And but for this parabolic motion, the universe will expand. So if you want, we can put it Big Bang. I like to use Big Bang. I don't like this word. I already explained why. So we'll discuss this later. And for parabolic motion, when you have exactly omega equal unity, so we will have dr by dt when the time when t tend to infinity, the velocity will tend to 0. So the universe will expand, but in the future, the velocity of expansion will go to 0. What is important that you can see that for this, for example, model, the universe expand with a deceleration. Please, per favore, I want to use Italian. Please write that in this case, universe expand with deceleration. And the third case, omega 0 less than unity, energy more than 0. In this case, we have also expansion. So this is a hyperbolic case. There's such a kind of universe called model of universe called open. And in this case, dr by dt, t tend to infinity, tend to constant. In classical mechanics, it's corresponds to hyperbolic motion. So in this case, the universe also will expand all time, but the future, finally, the velocity of expansion will go to some constant value, which usually call in celestial mechanics like a hyperbolic excess. So it was such a, I must say that it was such a joke. So we have 5 minutes. Such a joke that the density, all history of the universe, dynamical history of the universe, you can put as a text on T-shirt. Density is a destiny. So the density tell you how universe will evolve. And everything looks very simple from this case, but unfortunately, or fortunately, I don't know how to say, the reality is much more complicated. In the first, I would like to say that we can't use Newtonian. Of course, we can use permission, but it will be not exactly right to use it to describe the evolution of the universe. One point why, because when we speak about the evolution of the universe in the classical mechanics, I come back on this page and I put here arrow. Why? Because in Newtonian case, we consider the evolution of some volume inside of the space. In reality, in general case, we need to consider the evolution of the space itself. So please write. To consider the evolution of the universe, we need to consider the evolution of the space. It shouldn't be like this. So let's took some volume inside. In this case, when we put here galaxy on the surface, it will be two-dimensional space, which is inside of three-dimensional space. But our goal to consider the evolution of three-dimensional space. And this is, of course, already the first point outside of classical mechanics. The second, also, if you will use, for example, the formula of classical mechanics, you can discover that using the Hubble law, this one, you can discover that finally velocity of the object will be more than speed of light. So if the object far, so it's linear dependence. So later we will come with this problem that velocity became higher than speed of light, which is also tell us that the approach which we consider is not right to use for such a case. So, and if we would like to build a model which can describe the evolution of the object which is far from us, we need to use already relativistic theory. This is such a motivation which tells us that we need to start to work with general relativity. So, but what we discovered from the Newtonian mechanics, that in any case we can see that the solution of classical mechanics tell us that we come, and I put here error, that universe had some initial point when r equals 0. So it's already tell us some information about the possibility that in the past, since we discovered that r should be less, and less. So in this case, we come in such a kind of conclusion that universe in the past had a hot history when the distances between particles was small, and as a result, it was correspond to the hot evolution, hot time of the universe. This is what I would like to tell you. This lecture is about Newtonian cosmology. On the next lecture, we will start to work with general relativity. I will explain why we had this. We had a problem to formulate the new theory of gravity, which was a motivation. Which problem was Newton mechanics, and we start to work to work with tensor analysis, which is important to finally to write equation of gravity of Einstein. Do you have some question? Are you here?
Yes, we're here. Also, can I ask one question?
Yes.
So here we have rho 0 and rho critical, and rho 0 we know, and rho critical we also know because we know Hubble constant. So why exist these three different models? If we can.
No. In principle, yeah, it's a good question. So this is three model which give us equation. But we know, of course, from observations that in universe realized, of course, some of the three problems or model, and our universe, the space in universe is flat. So we exactly in this case. Even when we will consider general relativity, we will see that also in general relativity there are such a similar solution. But really, if we will calculate the average density in the universe for the present time and compare with the critical, they are equal each other. Space is a flat. It's, I tell you in advance, so we will. But again, all this model are without some additional part of the universe, which we call dark energy. With dark energy, everything will be much more complicated. So we will see how. But yes, really, this is for our universe, the critical density equal average density. And there is equation why we have this exactly this solution. I mean, why is the universe like this? Yeah. Did I give you an answer on your question?
Yes, okay, I understood.
So, okay, no any question? I hope it's no, it's understandable, or you're Okay, so I hope that you understand. So now we can close Zoom and we will meet on Friday. Yes?
Yes.
Okay, in this case, good day. See you on Friday.
Thanks.
I made a screenshot. Okay.
Hmm.
All right.